Okay, so we are going to be starting redox in electrochemistry. So this unit's broken up into two parts. We'll first talk about redox reactions and what the heck those stand for. Those stand for reduction and oxidation reactions. And we actually will get into that in the second video. Then the second half of this unit is electrochemistry. Electrochemistry is chemical reactions that produce electricity and that they use redox reactions. So that's how the two of them will relate to each other. The Statue of Liberty is on here because she has undergone a redox reaction, and we'll kind of circle around back to that at the end of the unit. All right, as I said, redox reactions stand for reduction, oxidation reactions. We're just going to talk about this briefly now and then in more detail in the second video. Redox reactions involve the transfer of electrons from one species to another. So one substance will be gaining electrons, one substance will be losing electrons. One substance will be undergoing reduction, one substance will be undergoing oxidation. So if we take a look at this reaction here, the sodium atom has one valence electron, chlorine has 7, and we know that sodium and chlorine combine together to make sodium chloride. So we see that the sodium will lose an electron, the chlorine will gain an electron, so therefore it's a transfer of electrons. The first skill that we need to learn in redox reactions is how to assign oxidation numbers, also called oxidation states. So we are going to need our periodic tables to do this. So if you don't have your periodic table handy, then pause the video and get it out. You could also pull one up online if you don't have a paper copy in front of you. All right, so oxidation numbers or oxidation states are a number that's assigned to every element in a compound or in an ion in accordance with certain rules. And we're going to go over what those rules are in a second. On our periodic table, in the upper right-hand corner, those are possible oxidation states. Now, this last statement here is a little bit confusing. So our oxidation numbers, by definition, are not the same as an ionic charge, but they often have the same numerical number. For example, sodium, Na, it will lose an electron to form a +1 ion. That's also the only oxidation number it can have. So they're often the same thing, but the definition of them is not the same. Ionic charge results from either the gain or loss of electrons. An oxidation number is really just an arbitrary number that's assigned to things within a compound just to keep track of the electrons. So what we're going to do now is we are going to go through and figure out how to assign oxidation numbers to things. The reason why we need to be able to do this is going to be step 1 of all of the problems that we're going to have for this unit. Okay, so our first rule for a neutral compound, the sum of the oxidation states must be equal to 0. So for example, if we have sodium chloride, Na, Cl. We look at our periodic table, we look at Na, we look at Cl. We see Na only has one possible oxidation state, so that's going to be +1. Chlorine would be -1. That would get us to 0. Or if we look at water, H2O. So oxygen is -2. That's its only possibility listed. Hydrogen is +1. It can also be -1 in rare cases. We'll talk about that in a few minutes, but it's usually +1 times 2 because we have 2 hydrogens. So that gives us a +2. That is what rule number 1 means. Okay, rule number 2, the oxidation state of any atom in an uncombined element is 0. So what I mean by that is if the atom is all by itself and it doesn't have a charge, then its oxidation number is going to be 0. So when Na was in a compound, it was +1. But if Na is just all chilling by itself, it's going to have an oxidation state of 0. So if we have iron all alone by itself, its oxidation state is going to be 0. And really, that goes along with this first rule here, because if it's got to sum up to 0, and the only thing we have is 0, or the only thing we have is one thing, it's got to be 0. One that's a little tricky is our diatomics, Cl2. So we still need it to equal 0, and both Cl's have to have the same oxidation number, so therefore it's going to be 0. It would be like in math, solving 2x is equal to 0, x would have to be 0. One little saying that I have for this is it's by itself, it has 0 friends. And this is an easy rule, but this is the rule that people tend to forget. All right, so rule number 3, oxidation state of a monatomic ion. So that means something by itself is equal to its charge. So if we have Na with a plus charge, that's going to be +1. So to recap our last 2 rules, if Na is all by itself without a charge, its oxidation state is 0. If we have it with a charge listed, then it would be equal to that charge. So another example of that, aluminum, all by itself, no charge listed, that's going to be 0. If we see aluminum and it has its charge there, +3, therefore its oxidation state is going to be +3. So if it's by itself, it's 0, unless it has a number there, then it will be whatever that number is. Okay, next one, for a polyatomic ion. So these are our things on table E, group of atoms bonded together, share a charge. Their oxidation states don't equal 0, they equal whatever the charge is. So basically, you add up to 0 unless you see a number there. If you see a charge there, then you're going to add up to that. So SO4. So we start by locating S and O on the periodic table. We see S has a couple of possibilities, so we skip over that for a moment. O only has one possibility, unless of course it was by itself, then it would be 0, but it's not by itself. So O has to be -2, but we have 4 of them, so that would give us -8 as a total, and we need to get to -2, so therefore S would have to be +6. And that is one of the possibilities listed for us, so that's a good indication that we probably did it correctly. So our answers would be S would be +6, O would be -2. Let's try another example, because that one can be a little bit tricky. So let's take another polyatomic ion off of table E. Let's do nitrate, NO3 -1. Okay, so instead of adding up to 0, we would add it to -1. So we go to our periodic table. We see N has a whole bunch of different possibilities. So we're going to wait on N. We're going to go to O. O has to be -2, unless it's by itself, then it would be 0. -2 times 3 gives us -6. Normally we total up to 0, but because we have a charge there, we have to total to that charge. So we have to total of -1. So therefore, our missing oxidation state would be +5, which is a possibility for nitrogen. So that's a really good sign that we did this correctly. So +5 -6, that's how we get to -1. And these would be our answers. So when you answer it, you're always reporting what they individually are, not what the total is. Okay, rule number 5 is kind of silly that I have this on here. Fluorine's always -1. If you take a look at the periodic table, it's the only thing that it can be. So that's why that rule is pretty silly. Unless, of course, it was by itself, then it could be 0. The rest of the halogens halogens are the group 17 elements. Those are typically -1. So for example, chlorine usually have that be -1, and then if the math doesn't work out, then change it to one of the other options. All right, if we take a look at hydrogen on the periodic table, we see it has +1 and -1 listed for possibilities of oxidation numbers. Now, it is almost always going to be +1. The only time hydrogen's not going to be +1 is if it's by itself, then it would be 0, or if it is with a group 1 or group 2 metal. For example, let's take a look at calcium hydride. So CaH2. So hydrogen is normally +1, but calcium's only possibility is +2. So if I'm going to get to 0, then hydrogen's going to have to be a negative number. So hydrogen's going to have to be -1, then times 2. That would get me to -2, and then that would get me to 0. There's no charge there, so therefore I'm trying to get to 0. So these would be my answers. So you are only going to make hydrogen be -1 if you have to. So if the math is not going to work out with it being +1, otherwise it's going to be +1, or if it's by itself, then it would be 0. Now we just have some examples. So you want to start by looking at the elements on the periodic table. So we have H2SO4. So we got H, we got S, we got O. A great place to start would be O, because O only has one possibility, -2. -2 times 4 gives us -8. The total is going to be 0 because we don't see a charge written there, so we're adding up to 0. Now, we just said that H is almost always going to be +1, so we could go ahead and give that a +1 times 2, because we got 2 of them, gives us +2. So then sulfur, in order for the math to work out, would have to have an oxidation number of +6. We check on the periodic table. That is one of sulfur's possibilities, so that's a great sign. Times 1 gives us +6. +8 -8, we got to 0. Yay. When you go to report your results, H is +1, sulfur is +6, O is -4. All right. For our next one, we have SO3 -2. The thing that's going to be different this time is instead of adding up to 0, we will be adding up to -2 because it is there. So we locate S, we locate O. O on the periodic table, O is going to be a better element to start with because it only has one possibility. I'm going to show you a different notation to do it this way. So O is going to be -2, S is going to be -6. So up here, I put my individual numbers. Down here, I put my total numbers. So this is just a different way to do it. If you like to do it this way, that's fine. Keep going like that. All right, I need to equal -2 this time. So therefore, S would have to be +4, because then +4 -6 would give me -2. To review, individual ones, which would be my answers, totals down at the bottom. Each oxygen's -2 times 3 gives me -6. I'm trying to add up to -2 because that's what the overall charge is. So sulfur has to be +4. All right, so pause the video for a second. See if you can figure out number 3 on your own. All right. So in number 3, we can start with either K or O because they both only have one possibility. It makes no difference which one you start with. So we start with K, +1 for the individual, We have two of them though, so that gives us a +2 total. Oxygen, -2 times 4 gives us -8. We're going to have to get to 0. So therefore, Cr needs to be +6. And that is a possibility for Cr, so that's a great sign. And these would be my answers here. K would be +1, Cr would be +6, O would be -2. Again, if you prefer to write it out like this, that's perfectly fine. Either way, we should get to the same answers. Last one, CrCl3. So put this one over here. We got Cr, we got Cl. So let's locate them on the periodic table, decide who we should be starting with. And you see that Cr has more than one possibility, so does Cl. So what we do there is we go to the rule that the halogens, group 17, is usually -1. So we can go Cl -1 times 3 would give me -3. So therefore Cr would have to be +3. And that is one of Cr's possibilities, so that's a great sign. So Cr is +3, Cl is -1. All right, so now what you want to do is go to the worksheet and try these on your own. Check them against my answers and make sure that you are good with assigning oxidation states. And then in the next video, we'll move on to talking more about oxidation and reduction half reactions.